I didn't know this one actually. Okay, so that was the first pass through the questions. Now I'm going to go all the way back to question 1 and give you 15 seconds a question to finalize your answers.
Yeah, you guys are definitely gonna win.
You said that Bethlee was like really
No, I didn't. I said put thinking caps on. That no, it's not. No.
Exactly what you say, you're dumb.
Yeah. I mean that too.
No, she's in the professional environment. She has to like got the mic on.
I am it's hot. It's hot.
Like as someone who's been
Each planet's orbit around the sun is an eclipse.
Sometimes we can just mention Dirty Dogs that's here.
Okay.
And the reason why the tall heaters are not in here, we got visited by the fire department today, and they are not. We're using them out there today, but they're going to be no longer. Those are like way past code. Like we didn't. They were here when
Gotcha.
nothing was here. So
Okay.
we're using them out there tonight. So that's why. But hopefully it's going to get warmer, so we won't need them as much.
Yeah, I think
And
it's
this
nice
works
out.
This works pretty nice.
It does, yeah, absolutely.
We just have to throw that question out. And then say eclipse.
Eclipse. Each planet's orbit is an eclipse. Okay, I have to mention $30. The $30. How do I work in Dirty Dogs to the next thing that I'm about to say? I did mention that on Facebook. So there's that. Okay. Are you ready to collect sheets? Yeah. Bethlee's mic'd up. I'm mic'd up. Okay. Well, anyways. Okay, I hope everybody got their trivia answers down. At this time, if you could bring your trivia sheets up to Sam and Rudy here at the front, along with your golf pencils. Please bring the golf pencils back. Please bring the golf pencils back. Bethlee? Are you ready? Are you excited? Well, great. This is gonna be great. What year are you again? She is a year grad student. She's second half year grad student. Technically, Jess, I think, is muting it for you when it's not needed, but if you want to make sure it's off, you would hold down this power button at the bottom. But probably won't keep it up. Oh, and this is the slidey dancer. Yeah, if you hold that down, it'll shut off. But let's go now. Okay, I hope everybody got their your trivia sheets in. We are going to move forward with talks for the evening. Is this loud enough? Can you guys hear me? In the back? Okay, great. Good to know. Also, I just wanted to mention that we do have a food truck here tonight, Dirty Dogs, if you want food. Okay, without further ado, I am going to introduce our first speaker of the evening. Bethlee Lindor is... Bethlee Lindor is a phenomenal graduate student at the University of Washington. She works with Dr. Eric Abel, and she is going to be talking to us today about finding ourselves, observational constraints of solar system exoplanet analogs. And she will teach you what all of those words mean, probably. So, please join me in welcoming Bethlee.
Hello. Wait, is this on? Do I need to speak?
Oh,
Okay, cool. Hello, hi, hello everyone. Welcome to my first Astro on Tap talk. Doing it. Yeah, today I'm going to be talking about how we can find ourselves potentially if we were looking for ourselves as an exoplanet. The main thing that you should know is that, oh, I forgot about the outline. Yeah, this is the outline, intro, motivation, background, yes, methods, you know, results, yes. Great, we all know that. The main thing that you need to know is that there are no solar system analogs that have been discovered in the universe aside from us. So I have here just a plot of the orbital period versus the mass of the known planets in the universe, and I have the red points are the solar system planets, and you see that the solar system planets are very unique amongst this jumble of points and data. So this really comes from the observational limits on characterization, and this can be really like broken down to two things. So the first is the transit depth. So I'm going to talk more about transit and transit timing variations later, but the transit depth is essentially like what happens when a planet passes in front of a star and causes a dip in brightness. That's all you need to know. And that dip in brightness gives us information about the radius of the planet with respect to the star. That is really good for radius measurements, but it doesn't really tell us anything about the masses of the planet, which is really important if we want to talk about the densities and potential for water and, you know, what kind of planet we're looking at. The other method that is mainly used for detections is radial velocity. So when a planet is orbiting a star, if the star like wobbles a little bit because of the gravitational force of the planet, then we can detect that as the radial velocity shift, and that gives us a constraint on the mass of the planet. But it doesn't really tell us anything about the size of the planet. So again, we can't really talk about the density, which is something that we're interested in for searches for life. This is very important in informing future surveys. So, for example, we have the Plato mission, the Nautilus mission, and the HabEx mission, and these are all missions that are that have the goal of looking for exoplanets and analyzing them and characterizing them and hopefully finding something that is Earth-like in nature. So that really begs the question, how common is our solar system? And on top of that, how do we look for systems that look like us, systems that look like ours? Well, this is a diagram of solar system objects, and what you'll notice here is Jupiter. Jupiter's great. Very easily detectable via radial velocity method that I talked about before. It's very strong gravitational force on the sun, great. But how do we learn about the inner terrestrials? How do we learn about Mars, Earth, Venus? Well, what we're going to do is connect exoplanet science and solar system science by using the solar system as a proxy. Now, the best way to find planets is to look around stars with known planets, obviously. And what you'll, hopefully that was obvious. And this is really going to address the questions of what can one learn about the solar system architecture if they weren't in it, and also like what how accurately can we constrain the known parameters of the solar system objects. One good thing to know is that a system with one transiting planet is more likely to have other planets transiting. And a randomly orientated observer is unlikely to see more than 2 planets transit. And this is especially the case for the solar system. So here is just a graph of the transit visibility zones of the solar system planets. So if there was an alien out there and they were looking at the solar system, these are the longitudes and the latitudes where they would need to be to see all of the planets in the solar system actually transit. And what you'll see here is that the researchers that did this work found that the terrestrials would be valid for thousands of years, like in these transit zones. The Jovian zones are valid for like hundreds of years. So this is because in actuality, these transit visibility zones aren't going to stay static. Like they're going to change due to the effects of the planetary interactions, planet-moon interactions, whatever is happening. So these are all technically moving. And knowing when the zones and how long the zones are going to be valid for is really important for using the solar system as this transit proxy. Well, one thing to note is that Venus actually would have a transit visibility zone that's valid for hundreds of thousands of years. So Venus is a very interesting object and very important object if we want to consider the solar system as a proxy. So the main parts that you should know about this plot is really these 2 points, which is where the transit zones of Venus and Earth intersect. So any alien in those latitudes and longitudes, that's where they would see the transits of Venus and Earth. And the reason why we want to look at, we assume that this alien can see Venus and Earth is because, well, Venus is going to be valid, again, for hundreds of thousands of years. So it's a great candidate for transits. And also, Earth, we are Earth. We are on Earth. We live here. It'd be nice if this alien could see us. And the probability of an Earth-Venus transit is 3.22 times 10 to the negative 4, which sounds really small, I know. But compare this to other planets that we've actually discovered. So I think Kepler 11 has 6 planets, and the probability of seeing all of those planets transiting is like way smaller. It's much smaller than this. So it's like 1 times 10 to the negative 4. So it's a little smaller, and we've seen this happen. So the fact that the probability of an Earth-Venus transit is low, don't worry about that. That's okay. So if we were to see Earth and Venus transiting, what would we see? So this is a little alien. I have a little alien. And this alien is looking at the solar system. Yay. And they would see, if Earth and Venus were transiting, what they would see is these types of transit. And I just have, over time, there would be a dip in brightness due to the passing of the planets in front of the star. And what matters here is these little dashed lines, and what they represent is the time of the mid-transit. Like, literally the time where the planet is directly in front of like the middle of the star during its orbit. And this is important because this time would actually shift due to the interactions that are happening between planets. So I have here this plot that just shows the transit number, like you can just think of it as time, so like time going forward. And during transits, the time that a transit occurs, you expect that to be linear if there was no other planets in the system. So that's where we have the line here. But what happens in actuality is that sometimes the transit would occur sooner than you expect or later than you expect, and that's just because of the interactions between these planets as they're orbiting their star. So here I just have the definition of transit timing variation. I know it's a big word. big words. It's just the variation in that mid-transit time, in that time of the transit that the transit is measured. And the definition of TTVs is just residuals to the linear fit that we have here on the right. This is a TTV formula. You don't need to know it. What you need to know is that it really scales in proportion to the masses of the companion planets, the eccentricities and orbital periods of the planets in the system, as well as the proximity to resonance. So for example, around Jupiter, like Io, Europa, those orbit in a resonance around Jupiter, and those affect the transit times of those moons. And so one thing to note is that the way that we measure the transit time is that we do a linear fit, a fit to a line. Great science, I know. And this fit is to the time calculated. So this is a time that you'd expect if there was no other planets in the system. So this just period times E, just an integer number, plus the first time of the period, first transit time, sorry. Okay, and hopefully, as I have demonstrated, multi-transiting systems are very, very valuable for understanding exoplanets. It's really good for detecting non-transiting planets, and you can also use it to compare and constrain densities of the transiting planets, as well as understanding the formation and evolution of terrestrial planets. And that's really good for looking for life in the universe. And here I just have a plot of the planet mass and planet radius of the TRAPPIST-1 systems. Yay, TRAPPIST. And TRAPPIST has so many transiting planets, and because a lot of these planets are transiting, we're able to get planet mass and planet radius measurements and actually look at their densities and how they compare to Venus and Earth. So you can see here that they're like a little bit more like puffy, like less dense than Venus and Earth, if I'm reading this correctly. Okay, now on to my observations. So unfortunately for us, I am not an alien in the middle of nowhere looking at the solar system. So I have to use simulations, yay. And what I really did was I simulated the observations over a number of years. So I here it only says 4, but like 30, 29, all the way going down to 15 years. And I use different like noise precision, so like the timing of that mid-transit, that is going to be like precise or non-precise or to a certain level. And so I set that level to be whatever I wanted it to be in the case. So the main thing to know about here is that I'm considering 2 cases. Case 1, 2 transiting planets only, Venus, Earth, Moon, barometer. Moon does not exist. Case 2, this is the real case with us, 2 transiting planets, 1 has a moon, Venus and Earth. And these simulations also include the effects of the non-transiting objects. So I'm taking the dynamical ephemerides from JPL, from NASA's JPL mission, and I actually simulate the positions of Earth and Venus over time, and I find when they'll actually transit, and here in the plot I just have a little line pointing to the line of sight that would be required to see their transits. And so I find those transit times over different observation spans. And I'm also like applying this analytical model, the TTV thing I was talking about earlier. And that really does a global search for the best fit model. I'll go into that later. And then I do something about Markov chains. You don't need to know that. So let me explain the global search for the perturbing bodies. So case 1, hypothetical. Well, we do a model 2 planets. We assume that there are only 2 planets in the system, and we find the best fit parameters for those 2 planets. We continue, we add 1 more object, 3 planets, great. We're looking for the 3rd planet, and in our case, we're going to assume that Jupiter is that 3rd planet because Jupiter is so massive, so it's more likely that it would have been detected either first or second technically how you define it. And then we add another planet, boom, 4 planets. So as we're adding objects, we're seeing how the data fits to the modeled simulations. So real case 2, we do the same thing, 2 planets, 3 planets, 4 planets, and then we do something special, we add the moon. And this is really great for seeing how well we can constrain the effects of the moon on Earth. So the moon, it's very small. It's only like what 0.018 Earth masses, but it has a very strong effect on the Earth, and it would affect the transit times. And you'll see that later, hopefully. Okay, so this is what happens when I do all these models, and I'm adding all these bodies to the modeling. So I have here the 2-planet model is in like blue, 3 planets in red, and then 4 planet is like the dash line. And what you'll need to see here is that the adding all of these bodies to the model improves the fit to the data. So on the left here is just the O minus C, like the observed transit time minus the calculated transit time. And that would be the TTVs, the transit timing variation. And on the right are the residuals. So like I'm taking these TTVs and I'm subtracting the observed, and I'm seeing how well the model fits our data. And the model with the 4-planet case really has like very, very small residuals, and that's a much better fit to our data. So this is with case 1. Now, if I do the same thing for case 2, I observe the same thing. Increasing the amount of bodies, the amount of planets really reduces the residuals. Something interesting to note here is that I also add the satellite that I was talking about earlier, and having the satellite in the model also increases the fit as well. So like the fits that are without the satellite are worse technically, like statistically here, than the fits that have the satellite, which is interesting because we want to be able to say that there is a moon there or there isn't a moon there. Okay, so this is what transit timing variations look like if you've never seen them before. So here I have just the TTVs for Venus and Earth, and this is when I'm considering 3 planets, Venus, Earth, and the Jupiter. What you'll really need to note here is that the contribution from Jupiter, it lasts over a really long time, which is expected because Jupiter has like a 12-year orbit. And what happens when I add a 4th planet? When I add Mars, there's a much better fit to data, as I was explaining before. And you'll see that like over a long period of time, Mars actually has really long-term effects on the transit times of Venus and Earth. That's what the graph is telling. And when I add the moon instead of Mars, one thing to note here is that the contribution of the moon to the Earth's transit times are on the same level as the contribution of Mars to Earth's transit times. So this is really showing that like moon's effects really as much as Mars, and Mars is much bigger and much further away. Okay, so how exactly do we search over a range? How exactly can we say that this is a detection? Well, we search over a range of possible periods for analogous planets, and what I mean by that is that we take, for example, something that's like Jupiter, and we place it as at a trial period. So say it's around like 11 years to 13 years, for example. And we see when, based on the signal, when there's a peak in the probability. And you'll see here that the peaks pretty much all agree with Jupiter's actual period, which is represented as the dashed line here. And here I just have the different years that I simulated as different colors, and you'll see how the detection of Jupiter depends on the amount of time that we're observing the transit times of Venus and Earth. And for the most part, as long as you have at least one period of Jupiter, you can detect Jupiter. Jupiter's there. Now, if we do the same for Mars, you'll see that there's a much wider range of periods that can fit the Mars-like object. So what's really important here is that there are cases where there are multiple peaks in the same time span. So multiple objects in the same time span can create a signal that is like a Mars object. And that's really sad for us. Okay, so on to results. So the hypothetical case. I have here just how the likelihoods show a unique Jupiter detection. So for 20 years of observation, you're looking at Venus and Earth transiting for 20 years, or 22 years, sorry. Jupiter is the only thing between 5 and I think it's 22 years that would be just like, there's a unique peak. Like there's no chance that it isn't Jupiter. So we will definitely 100% detect Jupiter. For the case of Mars, things get a little bit more complicated. So there's like these multiple peaks, or basically meaning that there's more solutions to the fourth planet. So a lot of objects could potentially be Mars. And if we look at the like posterior distributions, like the uncertainties of the masses and the properties of these objects, we'll see that we can very, very closely match up the masses for Venus and Earth. Like we get them bang on. The periods also bang on for Venus and Earth. The masses of Jupiter and Mars are also very consistent with what we're getting with the true values, so we don't have to worry about those. And there's a really good fit to this simulation. Okay, so what happens when we look at case 2, the real case with Earth and Venus, and Earth has a moon? Well, things get a little more complicated. Now there's like a higher uncertainty on the mass of Venus. There's also like a higher eccentricity for Venus and Earth. And we also see that the Mars-like object that is being detected has a period of 4 years. And that's a problem because Mars doesn't have a period of 4 years. So this object here, this high peak, corresponds to 4 years. And this object is a problem because it would be unstable over a long time scale. And that's really, and knowing that allows us to essentially throw out that information about the 4 years because it's not real. And now we get data and parameters that actually more closely correspond with the true values for Mars, and we love that. So now what happens when we add the moon to this? Well, the moon, we love it, it's great, and it's amazing. Like, it's a little off. Like adding the moon to the model is a little off for Mars. Doesn't get the correct period exactly, but it does improve the fit, and it is really dependable for getting the masses of Venus and Earth and Mars and stuff. In this case, though, the values for the period of Jupiter is like a little bit higher, like 4487. Yeah, it's pretty high. And like the uncertainties on those values are a little higher, but it is nice that the fit with the satellite is actually a really good fit compared to the fit without the satellite. Okay, so what does this mean for the future? Well, the main thing would be to note that this work was done with an analytic model, which means it's not actually, n-body, it's not as robust as we need it to be. So it'd be really nice to have to properly implement an n-body to compare this to the n-body. Another thing to note would be to simulate transit flux values to retrieve radius measurements, because with this method we only have mass measurements. We don't have any radii. And we can also analyze the effects of stellar variability. The sun is very variable, on small timescales, and it'd be really good to see how that affects our retrieval of the parameters. And then we can, okay, you don't worry about that. All right, so observational feasibility. Well, so remember Plato and Nautilus and those things that I was talking about before? Well, they're not going to be good enough to detect solar system analogs, I'm sorry to say. And so no known instruments have the baseline needed to detect an exoplanetary solar system analog. That is a system that has a gas giant and that has like multiple terrestrials and also has a moon. Plato won't have the required precision, but I think it has precision like a noise floor down to like 85 seconds, and all the simulations that I was talking about and that I showed, all the plots that I showed, had 30 seconds of noise. So 30 seconds compared to 85 seconds, that's a really big difference. The Nautilus mission might have the required precision, based on exactly how that pans out. It hasn't been built yet, so whenever that happens, please let me know. So regardless, all you need to know is that the potential mission would need to be long-lived. So it's interesting here because TESS, for example, was looking at a lot of planets. There's a lot of planets in the continuous viewing zone, and those planets would be great candidates for solar system analogs because TESS is going to be looking at them for a very long time in this continuous viewing zone. So key takeaways. Because of the transit timing variations of Venus and Earth, just two little planets, you can really correctly infer the solar system architecture and the masses and orbital properties of Venus, Earth, and the Moon, Mars, and Jupiter. Also, sad, but no known instruments have the baseline to detect systems analogous to a solar system, and you can correctly retrieve the correct masses. And you need to account for long-term stability when modeling exoplanet candidates. And this is the case for that fake Mars that we found that wasn't actually Mars. And it's very important to do a full stability analysis when we're modeling exoplanet candidates. I think that's all I have for you today, and I will take any questions. Yeah, that's great. Yes. Okay, the question is about that fake Mars. What is it exactly? And the thing with transit timing variations is that it doesn't really matter what causes the signal, the TTV signal. The information that we can retrieve from the signal depends on how well our model is. So my analytic model, for example, wasn't really good, and that's probably why I found that fake Mars that wasn't really Mars. So you don't really, it's not caused by Earth and Venus, it's probably just caused by something else, but we don't really know what it's caused by. It's probably just the accuracy of the model. Yes? Okay, the question was whether we, as a species, have the technology to build an instrument that has a baseline required. We 100% do. It's whether or not a person would dedicate 22 years of their life to this work to find a Jupiter-like planet or Mars something. Any other questions? Yes. Sorry? Oh, okay. The question was when I was talking about the probability of seeing a transit. So that was the overall geometric probability, just based on the radii and the period, the orbital period of the planets. So that's just overall three-dimensional. This is what the probability is mathematically. Yes. Wait, sorry. I believe the question was, when we see those multiple transits, how are we able to attribute them to the different objects? That takes a lot of modeling. So it takes a lot of like human hours, human work to actually analyze all these systems. So there's a lot of candidates for exoplanets, and the work to do all the modeling is just takes time to figure it out. Okay, one more. Oh, okay. The question was whether we find exoplanets that are all in the same plane as like the ones in the solar system. And we do, but that's only because of observationally, those are the ones that we are more likely to detect. So it's not just, it's not that they happen to be, like the ones that look like the solar system. Those are the ones scientifically we are more likely to detect. So that's why we detect so many of them observationally. Right? Right? Thank you. It was great speaking.
Yeah. 1 minute. Okay.
Okay. So we're gonna announce the trivia winners, and then we'll take an intermission to get you set up, and then we'll be good to go. Okay. Okay, so at this time, I'm going to tell you the trivia answers and the trivia winners. Just remember, if you are a trivia winner, please wait until the end of the second talk to come collect your prize. Okay, so let's get started with the answers. First question. It is true that places on Earth are so extreme they can be used as stand-ins. We call them planetary analogs, which you hopefully learned from the first talk. Sierra Blanca, Texas was the location of the Apollo astronauts' only pre-launch geology field training field trip. Kepler's first law. There's actually a typo there. It's supposed to be it orbits in an ellipse. Oh well. Around stars with known planets in the Milky Way is the best place to look for planets. That kind of seems like a funny answer. Okay. JWST orbits around the sun, just like the rest of us. The primary mirror on JWST is approximately 20 feet large. JWST does not have more mass than its predecessor, Hubble. JWST's mirrors are made out of beryllium. Discovery was the space shuttle that Hubble Space Telescope was deployed from. And Large Space Telescope was the original name. Astronomers are very creative, but don't worry, they use that name for other telescopes. So we do have large telescopes. Okay, are you ready for the trivia winners? Great. There's a four-way tie for first. All four of these teams only got 3 questions wrong. It's okay. And our trivia winners are Blue's Clues, Hallians. That's us, yeah. Nice, yeah. Aliens. Oh, aliens. Aliens. That's good. I like that. Okay. Tail end up front. What? What is tail end up front? Up front? Up front? Tell them up front? Okay. Okay. And the final winner is also a name that I cannot pronounce, but I'm going to try. The Groosters? The Crusters? The Goostiers? Okay, I hope that you know who you are from that. So now we are going to take a 5-minute intermission, which would be a good time to get a drink or a hot dog if you want. And then I will introduce our last speaker of the evening, Dr. Bruce Balick. Thank you.
telescope, no idea. James Webb, they're gold plated, right? What's that? No, but they're gold plated. So the surface is beryllium.
Yeah, and then there's like just a little bit of gold.
Oh,
Sorry.
no. I teach astronomy. I got to unteach that.
Oh no. Well, there's still gold there, so.
Those are the photographs.
Should we start this way? Yeah? Okay. Here's your slide advancer. Okay, welcome back. Welcome back, those of you that left. And I am back, those of you that stayed here. Just to make sure you guys can still hear me in the back, right? This is loud enough? Okay, great, thank you. So, our final speaker of the evening is Dr. Bruce Balick. Bruce has been with the University of Washington's Astronomy Department since the 1970s, and he even served a brief stint as chair of the department. In addition to that, Bruce is very well known for being absolutely pivotal in the discovery of the black hole at the center of our galaxy. So, Bruce is... So Dr. Balick is absolutely what I like to call science famous. And he is going to be telling us today about the James Webb Space Telescope taking over from the Hubble Space Telescope. So everybody welcome Bruce.
Excellent. I was telling Megan a minute ago, I've given this talk about 10 times. Never to a more boisterous audience. So let's try to have some fun. Let me make an admission. I had to boil this talk down from 45 minutes to 30. It's much easier to make a talk bigger than it is to make it smaller. So we're going to go like hell. First of all, let me just point out something that our graduate students are keenly aware of, along with everybody else in astronomy. In terms of tools for studying the sky, this is the golden age. In the last 20 years, telescopes across the entire spectrum, on the ground and up in space, have just ripped open our horizons, our research horizons. It is so much fun. I'll show you a picture a little bit later that illustrates what Hubble did to me, right? And it was, when you get an image from Hubble or Webb, you get an email. That's it. You have no idea when they're going to take the picture. You just get an email and they say, your data are in the archives. So the first thing you do is go to the archives. I mean, this is really exciting. You can't wait to see what the telescopes found. This has happened to me dozens of times, and the pattern is the same one. Absolute elation followed very quickly thereafter by sobriety. You get time on these telescopes not to take pretty pictures, but to understand the universe. And a picture can be pretty, but at the same time, completely puzzling. You'll see that when I get to the right slide. Anyway, thanks to you and your tax money, thank you for paying your taxes. These are some of the tools that are coming online. There's a laser in here. Yeah. This one I want to point out. This is a telescope that's going to survey, it's a 10-meter telescope, so it's among the largest on the ground today. And it's going to survey the entire sky, take pictures of the entire sky every 2 or 3 days in 6 different colors. It has the largest camera ever built in astronomy at the back end of it. it's really exciting. And I want to point this out because during my time as chair, our faculty helped to initiate this project. And now the project leader is someone that we hired while I was the chair. I am very proud of our faculty. So, all telescopes operate in pretty much the same way. Little particles of light that we call photons that contain almost no energy at all dribble down from far, far away. And we try to catch them and focus them to make an image or to get a spectrum. I'll get this right. So big is really important because the objects we're studying, in the case of Hubble and Webb, are at the outer edge of the universe, the edge of the visible universe. We're exploring the universe after the very first stars had formed. And they are very, very far away. How far away? 13.8 billion light years away. So their faint light has been traveling out in all directions for nearly 14 billion years. Right? And you need to see what we're looking at, you need big. But big costs money, and budgets are not big. And so Webb is the perfect example of a project that was very confident that it could be built. We were confident it could be built for $1 billion, and we ended up with a price tag of $10 billion. And that is sobering because almost every day you have to find a way to save money. That is the same as asking, what won't we do? And that's killing off your kids. All right, so here is Webb. But the light comes in from the left here. It's collected on a curved surface. This is the way all telescopes work. The telescope reflects the light usually to a second mirror up here. Webb has that. And that mirror redirects the light through a hole in the center of the primary mirror to the back here. And this is where the light is detected. Science begins not at the telescope, but right back in there. Now, why do we, 10 billion bucks, why do we spend that much money? I mean, if you ask an astronomer how much we should spend, you're not going to get 10 billion. You're going to get something a whole lot bigger, right? So, but why go into space at all? What's wrong with building a big telescope anchored to solid ground, right? Any, oh, the answers are right here. For one thing, the surface of the Earth is too bright. The lights from cities and now satellites are really compromising the ability of telescopes to do research, right? But that's not, I mean, that's just one reason, but it's not the big one. The big one is that little blue haze that you see around the Earth. The stuff we breathe, it moves, there are winds, there are instabilities, and we look at the sky as if we're looking through trees we're at the bottom of a swimming pool, there are ripples on the top, and we try to find the trees from the bottom. In other words, the atmosphere of the Earth defocuses the light that comes from so far away. These photons have been traveling for almost 14 billion years, and in the very last split second, they get a little bit mixed up as they come down through the atmosphere. So the problem is air. That's good news and bad news. Here's this picture I wanted to tell you about. This is called the Cat's Eye Nebula. You're looking at gas ejected by a star just in the astronomical time, just before it dies, right? So this phase of gas ejection lasts a few thousand years. Now, our best theories predicted that stars, since they're round, they would blow off their outer surfaces as bubbles, and they don't. And this is a great example of that. So the research question is, what shapes these things? What don't we understand about stars and the way they lose mass? So the best we could do until Hubble is on the left. And you know, we thought we were making very good progress, but that image here on the right that Hubble took, it just happened to be released by NASA while all of us were at a conference, a research conference overseas, and jaws dropped. The beauty, but yet the challenge. There are all kinds of devils in these details. So let's spend just a second talking about Hubble. It was launched in 1990, but when it went up, we learned, unfortunately, after it was too late to do anything about it, that its primary mirror had been perfectly shaped to the wrong shape. And for years, 4 years, we could not focus the camera. So the good thing about Hubble is that you can go up and fix it. And in 1994, the astronauts went up and put little tiny contact lenses in front of each camera. And from that point forward, Hubble was working better than its design specs. Here you see, I can't see from, sorry, the wrong buttons here. This is one of 4 instruments in Hubble. They're arranged in a circle around the back. There's a little 45-degree mirror that rotates back in the center of the telescope after the light has come through the primary. And that 45-degree mirror sends the light to the instruments. The one that the astronauts are installing in 2009 is a camera that I worked on from 1998 till 2009. And when they put that in the telescope, you can imagine that I was jubilant. A lot of other people were too. And that camera has turned out to be the workhorse instrument on Hubble. Now, Hubble was designed to last 10 years. It's at 32 years and going strong. It works in a part of the spectrum that the James Webb Telescope doesn't. So you have to think of these two as like red and blue telescopes. One complements the other. And there's no scientific reason to turn off Hubble. It'll last probably another 5 years. Its weakest link are the little gyroscopes inside it that steer it around. And they're mechanical. There's a wheel in there. And that wheel eventually, or the bearings on that wheel eventually give out. This is a picture that I took with Hubble. And I show it to you, A, because it's beautiful, but B, because last night at about this time, I submitted a paper I've been working on for 4 years, in which my team and I were trying to account for the incredible structures that we see here. So this is, last night was a big milestone for me. Thank you. So a year ago, Christmas, off went an Ariane 5 rocket. The Ariane 5 rocket has the biggest diameter. The US has no rocket at the present time large enough to carry the Webb telescope up into orbit. And as a part of their contribution to the cost of the telescope, the Europeans launched this. It was, I mean, you can imagine sitting in the living room watching NASA TV and realizing that $10 billion could go up in an explosion and that would be the end of it. NASA had a list of 340 things that were most likely to go wrong, any one of which would stop the telescope. The telescope went up, and 30 minutes later, we got our last look at the Webb telescope. Because at this point on, the Webb was headed almost a million miles away from the Earth, and we can't see it anymore. Right? At Hubble we can see, but not this thing. And by the time this picture was taken, that list of 340 things that could go wrong was down to, by a factor of 2, down to 170. But even so, the Webb telescope is way out there, and it lives in a place which is a delicate balance, right? The gravity of the Earth on the one side and the gravity of the sun on the other are perfectly balanced. If you nudge the telescope towards the sun, it'll fall into the sun. If you nudge it to the Earth, it'll fall into the Earth, right? So getting it to its proper place was a really tricky and delicate process. And not only that, the telescope built itself essentially along the way. So I think you all remember hearing about these things. It was an incredibly complex set of operations. It was like landing one of the rovers on the moon, dropping it in a balloon, right? I mean, the engineering behind this was absolutely unbelievable. And everything worked. Absolutely everything worked. In fact, we thought it would take, this telescope is steered by gas, little jets in the back of it. And so its lifetime is determined by how much gas is left after the telescope settled into its proper place. We expected to use about half of the steering gas, getting it in there, which meant the lifetime of Webb would be 10 years. We hardly used any of that gas, and the lifetime of Webb, unless something comes along and hits it, the lifetime of Webb should be 20 years plus. I mean, wow. Now, you've seen pictures of the telescope. There's some here on the left. This is the telescope. It works in the infrared part of the spectrum. You sense that as heat. And so the telescope can't possibly work if it's exposed to the sun. The surface gets hot, and the infrared radiation that's detected is from the telescope, not from outer space. So we built a heat shield here, roughly 5 mylar highly reflective layers. The telescope has to be guided so that the sun is at the bottom all the time, and the telescope is in shadow. And if that fails, I mean, that's what the steering gas is all about. And if that fails, the telescope can't do science. Now, why did we launch it? Well, certainly one reason was to keep making progress on things we've been studying from the ground for a long time. But that's not the way the Webb, I mean, Webb wasn't designed to do that. Webb was designed, oops, there's a slide missing in here. We'll use this one. Webb was designed, it's much bigger than Hubble, 5 times the collecting area, and it works in the infrared part of the spectrum. Now, we live in an expanding universe, and the expansion of the universe, first of all, makes distant things very far away. But at the same time, the expansion shifts the light, the spectrum of light that stars emit, right? That's the so-called Doppler shift, and you've all heard it. If you stood near some train tracks and a train approaches, passes you, and then goes beyond, the pitch of the train goes from to and that shift to longer frequencies, in effect, takes starlight, most of which is visible light, and shifts it into the infrared. And that the rate at which the universe is expanding, stars are really, really faint in the visible part of the spectrum, but they're still bright in the infrared. Let's, I think the next, well, okay. If there's time, I'll come back to this one. So on the right, well, these are 2 really deep images. The one on the right, taken by Hubble, 11 days. The shutter was open for 11 days, and those little photons drizzled down onto the surface and were detected. This is a Webb image, 12 hours. 12 hours taken this past spring. It's the same patch of sky. Right, so look at this little pattern right here, and you'll see it right there. But the Webb image is so much clearer. Right? So our hope with Webb is to explore the really distant universe. And that distant universe is a much younger universe. Just as we see the sun now as it was 8.3 minutes ago. That is, the distance to the sun is 8.3 light minutes. Just as we see the nearest star as it was 4.25 years ago. Just as we see the nearest galaxy like us 2 million light years away. Right? These things, let me emphasize the point that 2 million years ago means we're looking at a galaxy that was 2 million years younger than it is right now. We have no way of telling what it looks like now without waiting another 2 million years for its light to get here. So the point is, the further out we look, the further back in time we go. And that's the point of Webb, to go back as close as we can to the beginning. Now, when Webb was designed, scientists came up with what they thought stars at the first stars would look like. And that guided Webb's design and its cost. Right? So what we're really interested in are the little tiny dots in here. They're the faint objects. They're the galaxies with stars that have just formed. These blue and red circles here point to objects which we know to be at the visible edge of the universe. So the visible edge, what's the visible edge of the universe? The universe is 13.8 billion years old. Anything further than 13.8 billion years may have emitted light in our direction, but it hasn't come yet. Right? The furthest thing we can see is at a distance corresponding to the age of the universe times the speed of light. That's 13.8 billion light years. That's the edge of the visible universe. Is there stuff beyond it? You bet there is. Have we seen it yet? Nope. You'll have to wait until its light gets here. But that doesn't matter that much. The first stars are the first stars, and we can study them now and understand how stars originally formed and how galaxies originally formed. And that's a story which depends on what happened even before. Right? Starting minutes after the Big Bang, the universe had become somewhat irregular, and those irregularities run the movie forward, and those irregularities collapse, thanks to gravity, into these things that we can see. So there's a story behind each one of the galaxies that we can see with Webb, a story we're just beginning to understand. The first thing we found, though, from that picture, which was taken last spring, was that there were far more of these little tiny fly specks than we had expected. How many more? 100 times more. What does that mean? So 100 times more is interesting. It's a fact, but it's a lifeless fact. What does it mean? What it means is that galaxy formation, think gravity here. Galaxy formation took place far earlier and far more rapidly than we had expected. There's something really wrong with our ideas of how galaxies form, and it's going to be exciting to figure out what it is. It could be that the conditions in the early universe that bring mass together, or that supply the mass, the universe had more mass than we expected it to. That doesn't work. The universe, we know how much mass the universe has now, right? And so that's just not a viable path to take. Gravity may have been stronger in the past. Now, say that to Isaac Newton and he would choke. Einstein too, right? But it's these desperate situations like the one we're beginning to see here that really lead to breakthroughs. Right? It was the orbit of Mercury that didn't quite follow Newtonian gravity. That was one of the major reasons that Einstein stepped back from Newton's laws of gravity and said, wait a second, we have to retool these. And from that came general relativity, a new theory of gravity. Right? And it's observations like these, which will, we hope, we presume it always does work out that way, lead to gigantic scientific advances. Webb also took pictures of dying stars like the ones that I studied. This was one such picture. And I got a paper published along with some other people, obviously, within 5 months of this image being released. Our team looked at that image and said, well, we kind of understand the blue part on the inside, but the red stuff out there, what did that? What did that? So already we're beginning to rethink the ways in which mass is ejected from stars. It's so much fun. How am I doing on time? Oh, no. So Webb has taken a number of pictures, including the one on the right here of a fairly ordinary galaxy near us, whose Hubble image looks like this. This is the Webb image. These two are the same scale. Right? So this dusty, dark, dusty feature here is that one, because in the infrared wavelengths, dust emits its own light, just as embers after in a fireplace. Embers continue to emit light. The light shifts from the visible part of the spectrum, the fire, like those things, into the infrared. And so you're seeing on the right, the white regions are regions where dust is emitting. And the dust shows us that the galaxy is much larger in size than we might have imagined just from the Hubble image. There's a lot around the outer edge that doesn't emit optical light especially well, but really emits lots of infrared light. And one of the stunning features in this thing is this big hole right here. That's the sort of hole that might be produced by a massive star when it blows up and becomes a supernova, and the blast wave clears the gas out, leaving behind a big hole. We didn't know that there was a supernova there. In fact, all we see now is what's left of the gas that had been pushed around. The supernova has long faded away. But this gives us an idea of how much energy supernovae produce. Right? It isn't easy to move that much gas, and we can calculate the energy involved. Webb is aiming, of course, at the planets. And here on the left is Jupiter, as you probably have never seen it. Its great red spot is white. It's this thing right here. And you can see a tail around it, which is what you would expect, because that red spot is essentially a hurricane that appeared for the first time about 300 years ago. There were lots of people looking at Jupiter, and none of them recorded a red spot until about 250, 300 years ago. And we can watch it with Hubble or Webb, and it's turning around like a hurricane. It's right in between two weather bands. So hurricanes on Earth form between the equatorial, at the border between the equatorial zone and the temperate zone, and the same thing is going on here. We don't understand how the hurricane could last this long, which means we don't understand how it formed, and we don't understand how it gets its power. But that, again, is the exciting part of this if you're an astronomer. On the right here is that Uranus or Neptune? I forgot to. I'm pretty sure it's Uranus, but I'm not absolutely sure. And what you see here and there are aurorae at the magnetic poles of the planet, which is really exciting because the magnetic fields have a lot to do with the evolution of the planet. Think of it this way. Venus has no magnetic field. It's just one great big rock. Nothing much has happened on its surface in 500 million years. The Earth has a strong magnetic field which is anchored to a spinning core. And that core is releasing basically energy which causes convection to occur in the mantle of the Earth, which then breaks up the plates across the top and gives us plate tectonics. The spectrograph on Webb will allow us to take spectra of the atmospheres of planets and to find out what's in them. Now, I didn't put it in here. That's the last slide. Sorry. The infrared spectrum is where we're going to find the first signs of biological life. Right? There are no such elements or molecules seen in the planets in the solar system, with the exception of the Earth, where ethane and methane are chemicals that life produces, mostly cows, digestive systems in cows, are spewing out ethane and methane. And because ethane and methane don't last long, if you expose them to light, they disappear. Right, so on the Earth, we have this continuous source of fresh methane and ethane. And if we can find that in other planets, that's a really strong sign that life exists, or something that's really unusual. I mean, you can't prove that methane comes from life, but if it doesn't, we don't know where it comes from. All right, my last slide is this one. What happens next? NASA is hard at work developing a 50-year future of telescope development. The next telescope to go up will be called the Nancy Webb Telescope, and it's actually built, the mirror is a spare mirror left over from Hubble's construction. So a piece of Hubble will go into the Nancy Rubin telescope. But that telescope, thanks to better engineering, has designed in such a way, here's the biggest Hubble camera, and the Nancy Rubin telescope will have the equivalent of 18 of these things all working simultaneously. So for the first time, we can study large patches of sky in a reasonable amount of time. Beyond that, we're only limited by budgets and imagination at this point. The Webb telescope was such an amazing success that we're beginning to ask ourselves, what could we do with another one? What is the science that another Webb telescope could do that Webb can't do? So that means looking in a different part of the spectrum, designing the telescope to work there. There are many, many of these things. The cost is always the limiting factor. As I said, when I was on the design team for the camera for Hubble, we kept running out of money. We kept, and so what we wanted to do was moderated enormously by budgetary limitations. And so what NASA is doing is starting the design of 4 telescopes at the same time, hoping to find out where the technical problems are, and then putting their money on the most successful of those. It's a whole new way of moving forward, and it's going to be very exciting. So that's everything I have to say, and I appreciate your patience. You're a great audience. And I got to say, Megan is a wonderful MC, too. One thing you see right away, I'm sure you've all seen it, is that there's a smile on her face that just won't go away. Okay, is there time for questions? Okay. Now, because I wear hearing aids, I'm asking Megan to hear. Go ahead.
Yeah.
So you said that we know how much mass is in the universe. Like, how do we know that if there are some systems that are so far away we haven't really seen it yet?
So expansion of the universe, I got that much.
Yes. If we know how much mass is in the universe, how do we know that if we can't see systems that are further than?
Well, we can thank gravity for that, right? Gravity reveals both the mass that we can see, ordinary mass that makes light, and dark matter. And as it turns out, the universe contains about 5 times more dark matter than it does ordinary matter. We discovered that because things in galaxies were orbiting too fast for the mass we thought they had. We counted up the mass in all the stars in the galaxy. We used Newton's old theory of gravity, and we found that things going around the center were being pulled on by much more mass than we could see in the stars. And there are now several independent ways to show that dark matter exists. So gravity is the way we measure the mass of the universe.
Okay. Yeah. You,
How do you expect the pictures that Webb takes in 20 years to be different than the ones?
how do you expect the pictures that Webb will take in 20 years to be different from the ones it's taking today?
That be different from?
The ones that Webb is taking today. So how will Webb's pictures evolve over the years?
So Webb operates in a part of the spectrum.
A little closer. Here.
Thank you.
Yeah.
Webb operates in a part of the spectrum, I mentioned this before, that Hubble is blind to. Right? And every time we find a way to detect light that isn't visible light, radio light, infrared light, ultraviolet light, gamma rays, X-rays, every time we do that, we discover a whole new universe, one that we usually haven't predicted. Right? So when we design new instruments to break open a part of the spectrum, we base the design criteria on what we know, and those telescopes always show us what we didn't know, and that's really exciting.
Yeah.
These photographs, you're on the spectrum that's not visible from you now.
Mhm.
So you're colored. How do you decide how to color them?
That's a good question. So the question was, these photographs we're taking, they are not with light that's visible to the human eye.
Yes.
So how do we decide how to color them?
How do we decide how to color them? You know, the same is kind of true for Hubble. All it can do is take black and white images, right? And what you end up with is a series of images in different filters or different colors of light. And you go to Photoshop and you put your own colors in. It's that simple.
Okay. Other questions? Yeah. Oh, where was your paper published? Or what journal did you submit your paper to yesterday?
Where will it be published?
Yeah.
Well, first of all, if it's accepted, it'll be published in the Astrophysical Journal, which is the big research journal of the American Astronomical Society.
Is there a way to simplify how you found the sweet spot with the James Webb? I know you said that's complicated, but a million miles out to find that area where it holds it perfectly. Like, how was that determined?
I'm sorry, which sweet spot?
For the James Webb,
Yeah.
Where you guys found the right spot to put it.
How did
How
we?
did you
Oh,
find
to
that?
put it.
Yeah.
Oh, well, we've known about that since Lagrange, a French mathematician back in the 1700s. And as soon as we learned about gravity, it didn't take people long to realize that there's a point between two massive objects, which is where things are in balance. But it's a delicate balance. It's like putting a marble on top of steep mountain. I mean, one little push and that's the end of it. So, you know, when Webb went up within a month, let me back this up. There are 18 mirrors in Webb. It took us months and months to line them all up so that all 18 mirrors contributed to one image, right? And within a month, one of the mirrors was out of position for no apparent reason, right? And it turns out that a meteorite struck that mirror and pushed it a little bit. We pushed it back and everything's fine. It probably left a little divot behind, but it's so small that we can't see it. But this is the way, I mean, this is one way for Webb to meet its demise. Yeah, the big ones are really rare, really, really rare.
One more question? Yeah? Okay, yeah. So he's wondering how good are adaptive optics on the ground compared to space
Oh,
telescopes?
that's a wonderful question. So adaptive optics is the following.
The question was how good are adaptive optics on ground-based telescopes compared to space-based telescopes?
So think of these little photons are actually waves as they travel, right? And just as waves at the top of the swimming pool will cause the image to distort, if we're good, we can measure the distortion in the wave coming down, and then we can correct the mirror. We can push on the mirror here and there to straighten the wavefront back out. So that's the way adaptive optics works. And if we could make it work perfectly, there wouldn't be a reason to go to space anymore. But it never works perfectly. And there are other problems with observing from the ground, like heat and other things. But that's the big one. Good question.
Okay, we can give out another hand for speaking. Thank you. That was fantastic. Great job.
Thank you.
Thank you. I will have this for
Here,
this.
I'll get this.
Okay, so thank you guys so much for coming out to Astronomy on Tap tonight. Let's give another big round of applause for both of our speakers.